In this video, we're going to look at developing the Lagrange error bound from the mean value theorem as a way of better understanding this whole idea of the Lagrange error bound. So just to remember, the mean value theorem says that under certain conditions, that is, if f is differentiable on the open interval from a to b and continuous on the closed interval from a to b, then the derivative f prime of c is equal to f of b minus f of a over b minus a for some c in that interval from a to b. Well, we meet those differentiability and continuity conditions with our Lagrange error bound. So let's modify here a little bit our interval, and well, instead of calling it AB, let's call it from 0 to x, and we'll look at how this mean value theorem then could be applied to that. So we'll say that f prime, using the mean value theorem, f prime of c would then equal, our f of b is going to look like f of x, and our f of a is f of 0, and our b minus a is x minus 0. So if we multiply that x to the other side, we'll get f prime of c times x is equal to f of x minus f of 0. And if we solve this for f of x, then what we get is that f of x is equal to f of 0 and then plus f prime of c times x. So it may be hard to see in this small of a case, but this is really our Lagrange error bound for a 0th order Maclaurin series. Well, let's go extend this a little bit. Let's consider now, instead of using our f prime of c, we'll say f double prime of c will equal, and so now we'll need, for the f double prime to be a derivative, our function is going to be an f prime of x minus f prime of 0 all over x minus 0. See how we're now using the mean value theorem, but we're starting with the derivative function and getting to the second derivative. So once again, we'll multiply that x to the other side and get f double prime of c times x is going to be f prime of x minus f prime of 0. So we'll solve for f prime of x and gets that that's going to be f double prime of x, of c rather. Let me try that again. So we will get f prime of x will equal, I'm going to say f prime of 0 and then plus this f double prime of x at c of x. I'll get it right here eventually. At c of x. Now we'll look at this like it's a differential equation. We'll look at this like it's a differential equation and integrate both sides. So the integral of f prime of x is going to be f of x. The integral of f prime of 0, which is just a number, with respect to x, is going to give us f prime of 0 times x, and we'll get this f double prime of c, that number times x will be x squared over 2. And so and then we'll get some constant. And our constant, we're going to use the initial condition that f of 0 is equal to 0. And so we will get f of x. So plugging in 0 for x is just going to make these be 0, and we'll just get that c is f of 0. So we're going to get f of 0 plus f prime of 0 times x plus, and then here's our remainder term, the f double prime of c over 2, which is also known as 2 factorial, x to the second. Can you see that? That this is now a first order Taylor polynomial or Maclaurin polynomial, because we have the constant Then we have the derivative at 0 times x, and then here is our Lagrange error bound. So let's try this again. So last time we started with f double prime of c equals f prime of x minus f prime of 0 over x minus 0. We'll take it up to that next level. So now we'll say that f triple prime of c, again this is the mean value theorem, on the interval from 0 to x, and we're going to start with our second derivative function, which is differentiable, which we need to be differentiable as a condition for using our Taylor series. So now we have f triple prime of c is equal to f double prime of x minus f double prime of 0 all over x. We'll multiply that x to the other side and get f triple prime of c times x is going to equal f double prime of x minus f double prime of 0. We'll again solve for this time f double prime of x before we think of this as a differential equation. So I'm going to add that f double prime of 0 to the other side, where it will join that f triple prime of c times x, which is we're going to work our way into our Lagrange error bound for a second order Taylor polynomial. Let me slide this up a little bit. So we're going to integrate both sides, and we'll get the integral of the second derivative is the first derivative. The integral of the constant f double prime of 0 with respect to x is going to be f double prime of 0 times x, and the integral of something times x is going to be that something times x squared over 2 plus some constant of integration. We'll use an initial condition for f prime. That is, we would like f prime of 0 to be whatever it is f prime of 0 is. That's going to make that be that constant when we plug in the 0 for the x's. So now we're up to f prime of x is going to be f prime of 0, that's our constant, plus f double prime of 0 times x, that's a linear term. And then here's our soon-to-be remainder term, f triple prime of c, x to the second over 2. And again, we will integrate both sides. That will get us to f of x. This is what we want, is to solve for f of x. When we integrate the constant f prime of 0 with respect to x, we'll get that constant times x. When we get the constant f double prime of 0 times x, and we integrate that with respect to x, we'll get x squared over 2, which I'm going to write as 2 factorial. And when we integrate this f triple prime of c, x squared over 2, we'll get x to the third over 3 times that 2 that was there is going to make that 3 factorial. And then we'll get the constant of integration. And of course, we'll use f of 0 equals f of 0 for our initial condition. So plugging in 0 for all the x's is going to make that c, that constant, be our f of 0. And so here we have our, second order Taylor polynomial, Maclaurin polynomial for x equals 0. Maclaurin means that x equals 0. So here's f prime of 0. We're going to get our f double prime of 0, x squared over 2 factorial, and here's our remainder term, that f triple prime at some number c, x to the third over 3 factorial. We'll do this just one more time. And so this time, instead of starting with our f triple prime of c, we'll start with the fourth derivative at c will be equal to the third derivative at x minus the third derivative at 0 all over x minus 0. So again, this is our mean value theorem. We're taking our function f triple prime of x, and we're going to say on the interval from 0 to x, we know that its derivative, which is the fourth derivative, will be equal to our function, which is the third derivative, at b minus a over b minus a. That's where this is coming from. So we're going to take now the fourth derivative at c, we're going to multiply that x to the other side, and get f triple prime of x minus f triple prime of 0. We'll integrate both sides. The integral of the fourth derivative is the third, oops, I'm sorry, I didn't solve for x yet. Getting ahead of myself. So we will leave that f triple prime of x by itself. We'll add the f triple prime of 0 to the side that has our fourth derivative evaluated at c times x. We'll integrate both sides here. Going to slide this up. And so the integral of the third derivative is going to be the second derivative. The integral of a constant, f triple prime of 0, with respect to x, is going to be f triple prime of 0 times x. And the integral of our x is going to be x squared over 2. So that's going to be, whoops, I didn't do that quite right, of c times x squared all over 2, and our constant of integration. Our initial condition is the second derivative at 0 will be whatever it is we want that second derivative to be. And so that's going to make that constant be that f double prime of 0. So now we have f double prime of x is our f double prime of 0. That was our constant of integration, plus the third derivative at 0 times x, plus the fourth derivative at some unknown number c times x squared over 2, and we will integrate both sides. That will get us to f prime of x. We'll get the constant f double prime of 0 times x. We'll get f triple prime of 0 now times x squared over 2, and we're up to the fourth derivative here at c, and it's going to be x to the third over 3, making that x to the third over 6, which we'll write as 3 factorial, and our constant of integration. We'll use our initial condition that f prime of 0 is whatever f prime of 0 is. That's going to make that constant be f prime of 0, and we're almost done. Hang on here. F prime of x is going to be f prime of 0 plus f double prime of 0x plus f triple prime of x of 0 times x squared over, I'm going to call 2 factorial. And here's our error bound at this point in time, which is going to be x to the third over 3 factorial. And yes, we'll do this one more time. I'm going to slide over a little bit. So f of x is going to be f prime of 0x plus f double prime of 0 x squared over 2 plus f triple prime of 0 x to the third over 3 times 2 factorial is 3 factorial, and the fourth derivative at c, some unknown number c, and we'll get x to the fourth over 4 times 3 factorial is 4 factorial plus our constant of integration, and our initial condition is that f of 0 is f of 0, and so we will say that f of x is f of 0 plus f prime of 0 times x. This is looking just exactly like our Maclaurin series, which it is. Whoops, that's 2, and 2 is 2 factorial. Here's our third derivative at 0 times x to the third over 3 factorial. And here's our fourth derivative at some unknown number, x to the fourth over 4 factorial. And once again, we can see here is our Lagrange error bound for our third order Maclaurin polynomial. I don't know, I hope that helps. It was kind of an aha moment for me when I saw that.